This is outcome 38, reaction energetics. I'm going to use this reaction up here, CH3Br plus cyanide gives us acetonitrile CH3CN plus bromide ion, Br minus, to exemplify what we're talking about in this outcome. So if I take and think about it, I know that these reactants have an energy associated with it, and the products have an energy associated with it. Unfortunately, I don't know what those energies are. I can never find out exactly what they are, but I can get around it another way. And we've already talked about this, and by the way, energy is associated with enthalpy, H. For right now, we're going to talk about it in terms of enthalpy. Okay, it's not exactly that, but you know about it. And so I can measure delta H of reaction from heat loss equal heat gain, Q lost or Q gain. And there's a negative sign in here. You've done these type of calculations, and we calculated temperature change. So I can work the reactions backwards and calculate delta H from temperature change. We're not going to do this, but you need to understand that we can get it that way. So instead of calculating temperature, I calculate enthalpy. We can never measure the enthalpies of the products or the enthalpy or energy of the reactants exactly, but we can get the delta H. That's an important concept in here. So if I make a plot of energy or enthalpy, and you will learn other ways of stating it. It's really Gibbs free energy, but we're using it synonymous with enthalpy in this class. And I put down here reaction coordinate, and I'll explain what that means in a few seconds. It really is the amount the reaction has gone, okay, or where it's at in the process of reaction. So if I put my reactants down here, I can either have reactants here, and I'm going to shortcut that as an R, or I can have products down here. I'll put them in blue, products. And my delta H of reaction would be this distance. And that would be an example of an exothermic reaction because energy was given off during the reaction. I went from here and I went down. I released energy. An example of an endothermic reaction, if I make the same plot, energy and reaction coordinate, and in this case I would start maybe same place. Here's my reactants and my products up here. We'll put them in green this time. Would be up here, so I have products up here, reactants down here, and this would be an example of an endothermic reaction. Write it in, endothermic. And we've talked about this already, so you understand this. On this side I have exothermic. So that's our situation right now. This should all be review. Linear race. Now the question becomes, what happens in this area when we're going from reactants to products? So if I look at CH3Br, I have something like this. This is a Lewis dot structure. An H, and I'll draw it in 3 dimensions, a bromine, an H, and an H. Now I'm going to talk about this cyanide ion coming in, and you'll talk more and see more of this next semester. The bromine leaves and it takes its electrons with it. You don't have to be able to do this, but I want to explain. And the Cn minus is going to come in from behind and attack the carbons. Is one way that these reactions can happen. So that's what's going to happen to get from the reactants to the products. When it does this, it forms a structure that might look something like this. This is the current state of the theory. The hydrogen out front, a hydrogen back behind, and then I will attach in orange my bromine here, and I'm putting dotted lines because it's breaking, and I'm going to attach a cyanide in here, and I put dotted lines between two carbons because it's forming a bond. Now, if you look real closely at this thing, it's a mangled mess. Actually, it's really well drawn this time. But the point being here, this is a 5 bonds to the carbon. It's really 1, 2, 3. And if I can think about these as half bonds or full bonds, but I have a 5 coordinate carbon, and you guys know that really doesn't exist. So this is an extremely high energy state. It is not going to set there. So what has to happen in our energy diagram, because of this, this thing we formed here, which I'm going to call the transition state, transition complex, transition state, molecule, transition complex. So I got to go up in energy to form this. So as this bromine is leaving, this CN ion is coming in, forming a bond, making this high energetic system. So as the CN comes in, it starts to go up, 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 up. And at the very peak, I form this transition complex. It's sometimes called the activated complex. So it's way up here, high in energy, and then it drops back down. And when it drops back down, it's going to the product. So the bromine completely leaves. It's gone, and we form a bond. So I'll draw it down here. So now I have C, H, 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 and I have my cyanide molecule back in behind here. Okay, so we're back to cyanide ion. We're back to something we recognize, and that would be our products, and that's a lower energy state. Excuse me, I want to label these. So this is called the transition state, and the molecule is called the activated complex. Complex. In very high energy state. The energy to get to it is called the activation energy. This energy from the reactants to the transition state, that change in energy, is the E sub A, which is activation energy. I'll write it down here in the bottom right hand corner. Activation energy, labeled E sub A. So let's talk some more about this now that we know what we're looking at. Let me erase. Okay, so here we go. We have the activation energy labeled again. This is the transition state. TS for transition state. Activation energy is this difference. These are the energy of the products and the reactants. Okay, so it turns out that if you change the temperature of a reaction, then the reaction will proceed faster. That's because you're giving the reactants more energy to get up over this hump. Okay, and so that's what we do. If we do the reaction at different temperatures, say temperature of 100 C, 200 C, 300 C, etc., the rate will increase. And I'm just making these numbers up. The rate will go from 300 to 1,000 to 1,200. Well, actually, let's make this about 2,000 on that. Now, we'll find out in a future outcome how to deal with this rate and a thing called a rate constant. So it turns out that the rate constant, which is proportional to the rate, follows this law. The natural log of the rate constant, K, is equal to the natural log of A minus E sub A, the activation energy, over RT. That describes this graph, and specifically this area right here. Okay, and it allows us to get at the activation energy. Alright, so now we're ready on how to do the outcome. Let me erase. So what you're going to be given is you're going to be given a graph of the natural log of the rate constant versus 1 over T in Kelvin units actually Kelvin to the -1. And you're going to end up with a slope that looks like this. I'm just making the data points up. It'll be a baseline fit to the data. And from this equation, log K equal log A naught minus E sub A over RT. This is the form y equal mx plus b. This is y. This is the intercept b. 1 over t is x. That's 1 over t. And the slope is negative e sub a over r. So from the slope is equal to negative e sub a over r, so we can solve for e sub a. Slope, negative slope times r. We also can find a naught. A naught is called the pre-exponential factor, and we can solve for it. The natural log of a naught is equal to the intercept, and so e to the natural log of a naught is equal to a naught, which is equal to e to the b. And so we can find the intercept, a naught, the pre-exponential factor from there. So that's one thing you're going to have to do. You have to determine e sub a from this graph, and you're going to have to determine a sub naught from this graph. All right. So the final thing you need to do is make a graph of energy. You'll need to label the axis versus reaction coordinate, sometimes called profile or reaction profile. I think I have it labeled for you. You'll get this graph and you'll just have to make it. And you'll be given the delta H. So let's give you the delta H. Delta H of the reaction. You'll be given a reaction. Delta H of the reaction equals, say, negative 300. And you've determined, let's put units, kilojoules per mole. And you've determined the activation energy to be 150 kilojoules per mole. And we want you to make a diagram like I've drawn. So I'll put my reactants here, label them reactants. And this is exothermic, so I'll put my products down here, products. Remember, it's exothermic. And my activation energy is 150, so this change right here, let me put it in orange, is delta H of the reaction, and it's equal to negative 300 kilojoules per mole. You'll have to label everything. We have an activation energy here that's 150 kilojoules per mole, so this distance here will be labeled the activation energy, and it is 150 kilojoules per mole. Hence this distance here, if I can get my pen to work there. Okay, and we'll label this. So we've labeled the activation energy over here, and that's this distance from here to here. We've labeled the products, the reactants. We've labeled delta H. You also need to label this the transition state. Transition state, also called, and the molecule is called the activated complex. So that's what you have to do. Probably the last 7 or 8 minutes of this was the most important part, how to calculate E sub A from your value of E sub A and the given delta H value. These two, you can make the graph and label everything.